Hello, I'm Álvaro Calafell, and this is the second part about the impact of harmonics in electrical installations. This part will present the impact of harmonics on transformers. In the last video, the impact of harmonics on capacitors was presented. In the present video, I will present the impact of harmonics on transformers. The impact of harmonic on transformers can be summarized in two main issues. The first being the extra losses in the core and the heating of the conductors, which produces a reduction in the expected transformer life. These extra losses are due to the Joule losses, the winding eddy current losses, and the stray losses. The transformer heating due to the extra losses is considered by means of the K factor. This factor is a weighting of the harmonic load currents according to their effect on transformer heating and is calculated from the expression below, where the current corresponds to the root mean square value of the nonlinear load current of the harmonic K in Pu referred to the transformer rated current. A K factor of 1 indicates a linear load, so no harmonics are involved. The higher the K factor, the greater the harmonic heating effects. Once this K factor is calculated, it is used to determine the transformer's rating to correct the nominal power of the transformer in presence of harmonics injected by nonlinear loads. The K factor is used by transformer manufacturers and their customers to adjust the load rating as a function of the harmonic currents caused by the loads. When a nonlinear load is supplied from a transformer, it is sometimes necessary to derate the transformer capacity to avoid overheating and subsequent insulation failure. As an example, imagine the following transformer supplying the nonlinear load with the harmonic current shown in the table. The nominal power of the transformer is 100 kVA, and we are going to analyze if a resizing is necessary due to the nonlinear load presence. First, the nominal current is calculated, and subsequently, the square of the harmonic currents in Pu referred to the nominal current of the transformer are calculated. Each current is multiplied by the square of the corresponding harmonic, obtaining the values shown in the table. By adding all the terms, the K factor is obtained. This factor allows to review the nominal power of the transformer. In order to do this, we must plot the K factor in a transformer rating curve, obtaining the capacity factor, which allows to determine the correct nominal power of the transformer in presence of nonlinear loads. To obtain this value, we must divide the nominal power by the capacity factor calculated before. In this example, we can observe that the nominal power of the transformer should be increased in order to consider the extra losses due to harmonic current presence. If loads are linear, the K factor is equal to 1, and the capacity is equal to 100%. In office areas with compact fluorescent lamps and large computer rooms, the K factor is usually between 4 and 9. The second impact of harmonics on transformers is the difference between the outer and the inner currents in a transformer. By considering the classification in direct, inverse, and modular sequence of the different harmonics, we can study the following example. Take a delta Y transformer supplying 3 single-phase nonlinear loads which consume all the other harmonics. These harmonics also flow through the secondary Y windings, and all of them are reflected in the primary delta windings by consuming the transformation ratio of the transformer. However, the triple harmonics do not appear in the primary of the transformer because they are cancelled. Therefore, we only have the fundamental, the fifth, the 7, and so on harmonics. These harmonics are equal to the square root of 3 divided by the currents in the primary winding of the transformer. The difference between the harmonic currents in the primary and in the primary windings of the transformer produce that the current in the primary cannot be used to characterize the operating point of the transformer, because this current can undersize the real current flowing through the primary windings of the transformer. In other words, these harmonics from the primary current do not reflect all the harmonics flowing through the primary delta winding in the transformer. Therefore, they cannot be used to determine the harmonic content inside the transformer. If we calculate the ratio between the root mean square value of the primary delta winding current and the primary current From the harmonic spectrum seen below, we obtain that the root mean square value of the primary delta winding current is 1.23 times greater than the root mean square value of the primary winding current, obtained from the typical relation between the primary current and the primary winding current.